Hey folks, this is Sunil from Intel, and in this presentation I'm going to talk about enabling asynchronous Paravirtual IO in OVS. Now that's a long title, so let me try to address them in chunks and then combine them to realize the big picture. First, let's see what Paravirtual IO is. So Paravirtual IO is a virtualization technique which enhances the VM IO performance, and virtIO being the standard for it consists of a front-end and a back-end. Front-end in the VM and back-end in the hypervisor. These two entities talk to each other by copying packet buffers, and copying data between the front end and the back end can become a CPU hotspot. So if we can offload this copy to other hardware, we can save CPU cycles and use it for other tasks. Talking about offloading, there are two modes we can achieve this. First one being synchronous mode, where CPU offloads some tasks to the hardware and waits for its completion and then proceeds to move on to the next task. Second one being asynchronous mode, where CPU offloads the transfer to hardware but doesn't wait for its completion. So CPU can do other stuff while hardware can copy parallelly. Let's now check what APIs DPDK supports to facilitate this. The vHost library supports these two APIs, submit enqueue burst, which is used to enqueue the packets asynchronously, and poll enqueue completed, which allows us to query the transfer status of the copy. These two functions internally call a couple of callbacks which needs to be implemented by the application, that is OVS. Now, these callbacks can be bound to a VID-QID pair using channel register and unregister APIs. And of course, we must set the vHost-user async copy flag to enable the async capability for the vHost device during driver register. As you might have noticed, there is only enqueue API available at the moment and no DQ API. This is yet to be implemented. Now, in order to implement these callbacks, we must utilize a hardware to offload the copy operations too. And in this case, we took Intel QDT as an example, which uses IOAT PMD in DPDK. So IOAT PMD supports these APIs to make the device setup on the control path, info get, configure start, and raw dev stop. And for the data copy, it supports IOAT enqueue copy and perform ops, and another API completed ops in order to query the QDT transfer status. As you might have guessed, in these callbacks, we will utilize these functions. So going back to the diagram from slide 1, where does all this fit in? It fits right here on the enqueue path, that is from the back end to the front end. Another important point to note is that these APIs, both async and IOAT, are both experimental in nature. Let's now compare the CPU synchronous pipeline and the QDT asynchronous pipeline. First, we look at the CPU pipeline. Here we read the descriptors, we enqueue the packets, that is copy the packets, and then free them. And to compare with the QDT async pipeline, the first step remains the same, that is to read the descriptors. Then we select the QDT and enqueue the packets, which is where we are essentially calling RT-IOAT enqueue copy API, and of course we repeat this for the entire batch. And then we ring the doorbell, which is where RT-IOAT perform ops API is called. And then we free the packets. Now there's a reason why I didn't connect these two blocks. Let's look at why a bit later. Now, offloading the copy for small packets can have a bit of overhead as compared to CPU copy because of configuring the DMA and small chunks being copied. So in these cases, we would still want to use the CPU pipeline. So we need to decide in order to choose between the CPU pipeline or the QDT pipeline based on the packet size. That's where async threshold comes in. This parameter can be set by the user during callback registration. It's important to note that the decision to choose the pipeline is done by the vHost library and not at the application level. So how is this async threshold used? Let's take an example. First, let's consider a typical PVP scenario where there are two physical ports, that is DPDK ports connected to the traffic generator and two vHost ports connected to the VM. Let's assume there is an L2 forward application running inside the VM and the hardware block here represents the QDT. Now let's assume the async threshold in this case is 512 bytes. Let's see what happens when a packet of size 256 is received. Since 256 is less than async threshold, it takes the CPU pipeline. The same is reflected in the PVP diagram as well. Now let's consider a packet size of 1024 is received. Since 1024 is greater than 512, it takes the QDT pipeline. So how can we enable the vHost async mode in OVS? In order to enable this, there is a user configuration option called vHost async copy support, which can be set to true before the vSwitch daemon is started. After setting this, you can add the vHost async attributes, something like this. So what are these? So txq number, the dbdf function, and the async threshold for that specific queue. Now before you specify the PCI ID for the QDT, it must be bound to a user space driver like VFIO or IGBUIO. Now when this option is set, you can see in the log there is the specific message which allows the user to confirm whether async copy is enabled or not. Now let's see the challenges we faced while implementing this. There were 3 to 4 main challenges we faced, like the check completed copies callback requires to return the number of packets sent, but the RT IOAT completed ops returns the number of segments sent. So what are these segments that I'm talking about here? For large packets, the vHost library splits the packet into multiple chunks called segments. These segments are then enqueued onto the QDT. Hence, the IOAT completed ops API will also return the number of segments sent in the transfer status. So, it's not a simple forward of the return from IOAT API to the vHost library. Coming to the second challenge. Since QDT copy is asynchronous in nature with the CPU, QDT might still be copying the packets when the enqueue API returns. So when and where to free those packets then? Note that this also depends on the hardware used. This is exactly why in the QDT pipeline diagram, the free packets block was not connected to the rest of the pipeline. The third and fourth challenges sort of go together. The QDT channels are currently statically mapped to the TXQs as shown in the previous slide, and there are only a handful of QDT channels per NUMA, so we have to use them cautiously. Now let's take a look at the possible solutions for these challenges. For the first problem on returning the number of packets, we can have a packet tracking mechanism where we keep track of the number of segments enqueued per packet and match them with the completed ops return to get the number of packets sent. For this, we will require a buffer to keep track of the segments per packet. For the second problem on when and where to free, there were multiple approaches tried. Let's take a look at them one by one. First solution would be to wait until all the packets of the current batch are freed and only then we process the next batch. So I'm talking about waiting in the function DPDK vHost send. But here's the problem. CPU is not doing any useful work. Moreover, this beats the purpose of async. So let's try another approach then. Now, we don't wait, but we just free the packets inside the same function after sending, that is enqueue. The underlying assumption is that packets not freed in the current iteration will be freed in the next one. So what's the problem here then? We must call poll enqueue completed function regularly in order to flush the word queue and the QDT ring. So if not many packets are freed by the next iteration, we could run into word queue and DMA ring being full. Also, the packet sent in the last iteration would not be freed at all. Moreover, in case of dynamic TXQs, what if the same TXQ is not at all used from the next iteration? So, what else could we do? We can free the packets outside the send function much later. But where? To decide this, we must consider a couple of things. The candidate function will have to have access to the netdev and txq ID. Also, it must be regularly called in the PMD. A good contender would be the PMD flush output packets at the dpiff level, because it's called regularly in the PMD and also has access to the netdev and txq ID. So we free once after the PMD flush output on port, which happens to be the function where the packets are sent, and then call free continuously for the netdev and the txq ID between bursts. But this is not an elegant solution. Why? This will require access to spin locks on txqs and as a consequence has high CPU usage around 60% in perftop. Moreover, directly calling free here breaks abstractions. So fair, let's try to solve these problems now. To reduce the CPU usage and avoid breaking abstractions, we can have a callback at the netdev level, that is, instruct netdev class something like this. This will cause free to be called only for vhost ports which has this function register. We could also avoid calling free if there are no packets to free instead of simply polling to check the status. So how can we achieve this? We could have tracking at the netdev level itself, perhaps a bit mask for each queue or even at the PMD level. When we tried this, the CPU consumption came down to around 7% as compared to the previous 60. But is this it? Not so soon. What if dynamic TXQs are used and we get the same problem like we discussed before? This is something we are still exploring. Now coming to problem 3 and 4 on limited QDT channels. Possible solutions could be to have a pool-based mechanism to allow for sharing the QDT channels among the TXQ instead of tying them to one single port and queue. So what's next? There is a bit of future work to do, like to further investigate on when and where to free the packets, support the DQ operation, support sharing QDT among the vHost queues and ports, introduce debuggability, and of course update the documentation. Here's the link to the V1 patch sent out. We would love to hear feedback on this from the community. That's pretty much I had, folks. Thanks for your time. Let me know if you have any questions and feel free to reach out to me in case of queries. Thank you.